Yep, that's good. Yep.
Can you guys hear me in the back there? Good.
We all ready?
Yep.
Okay. You guys hear me in the back? Julia, can you hear me? Okay. All right, I'm very happy to introduce Ben today. He's going to be presenting his master's research. I'd like to give a little bit of an introduction on kind of his really interesting journey to get to this point. First of all, Ben's pretty much a local, born and raised in Wisconsin. He did his undergraduate here. He graduated in 2017 from this department, did his undergrad here, and then he went off into the private sector, still staying local for a few years, so really building up his programming chops, which have become super beneficial, in his research going forward. While he was here as an undergrad, he worked with SSCC's Proud Severe group and was on a paper with that group while he was here. And then he decided to come back. He started here in 2020 in the summer with the goal that he was going to go with me to the field off the west coast of Africa for a field campaign, and obviously that didn't happen. So Ben came and we said, all right, there's got to be some earlier field campaign data we can work with as we prepare for the project. So a lot of this work is from that other data set that he was able to use. But thankfully, we eventually got into the field, and Ben was a really integral part in the forecasting component of the CPEX-AW field campaign in 2021, which he was also a large part of changing the fact that instead of West Africa, we had to go to St. Croix because we weren't allowed in West Africa. So Ben was part of the group where we all had to change our objectives and the forecasting strategy and everything. So he spent a lot of his graduate career learning very quickly how to be adaptable. And so a lot of his experience comes into play here as well. And then that project got unfortunately cut very short. And he was a really integral part in the final phase of the field campaign when we finally got to go to Cabo Verde this last September, where Ben was now leading the forecasting team. He was participating in the flight planning, serving as a mission scientist, directing drop zones in the way that he wanted for his analysis, which was a really unique experience, analyzing drop zone data. I mean, he wore all the hats, and I don't know that he actually slept at all, maybe the entire month in Cabo Verde. But I really want to emphasize all the amazing work Ben's done outside of the research, but in kind of bumping up his leadership skills in the field, which haven't gone unnoticed from headquarters and helped encourage him to stay on for his PhD. So with that probably long introduction, Ben, take it away. Let's hear about your research.
All right, yeah, thanks Angela for the introduction, and thank you all for coming today. So today I'll be presenting the research I've been doing over the past 3 years for my master's thesis on relationships between tropical oceanic convective structure and the near storm environments as observed from the recent NASA CPEX and CPEX-AW airborne field campaigns. So just to start off with a quick background, tropical oceanic convection is a prevalent feature of the tropical atmosphere, as we can see here from the boreal summer precipitation climatology here from Powell 2015. And as such, tropical oceanic convection is an important driver of both the regional and global weather and climate through things such as its redistribution of atmospheric mass, momentum, heat, and moisture, its influences on the global radiation budget, particularly its cloud structures, particularly in cirrus. Its precipitation alters upper ocean buoyancy and thus upper ocean circulations. And additionally, the cold pools associated with convection can initiate new convection. They significantly alter the characteristics of the planetary boundary layer, and they also enhance air-sea exchange as well. So with tropical oceanic convection modulating tropical weather and climate, accurate tropical oceanic convection representation and parameterization is critical for the success of weather and climate modeling efforts. However, despite its importance, challenges persist in modeling tropical oceanic convection, partly attributed to lack of understanding of how tropical oceanic convection relates to its near-storm environments throughout storm system life cycle. But studying near-storm environmental relationships is difficult because it requires frequent, high-resolution measurements to capture fundamental small-scale convective processes, features, and environments. And in-situ data collection, mainly from field campaigns, is the ideal means of collecting these high-resolution measurements, but field campaigns are historically too few and far in between. That being said, many studies using field campaign data have looked at tropical oceanic convection relationships with various environmental metrics, And a popular study metric is wind shear due to wind shear's ability to, say, influence convective development and sustainment through the separation of convective updrafts and downdrafts, particularly with regards to single core or isolated cellular systems. And also low tropospheric wind shear's interactions with convectively generated cold pools in accordance with traditional RKW theory, where the balancing of the low tropospheric shear and cold pool propagation speeds can sustain convective systems through vertical tilting and through the generation of new convective elements as well, even though traditional RKW theory doesn't always apply to tropical convection. Anyways, these wind shear studies overall are predominantly centered on quasi-linear convection, and they found that generally the greater the deep layer speed shear, the larger and more intense the convective systems tend to be. And this is mainly based on observations from the Western Pacific Basin and also model reanalysis studies of the broader oceanic tropics. We can just see an example of that here from Island Bend in year 2015, where we see as speed shear increases in the deep layer, both the anvil width and the number of convective cores tend to increase as well. Additionally, studies have found that greater low tropospheric shear is associated with more perpendicularly oriented convection relative to the low tropospheric shear vector. Again, this is mainly based on studies from the Western Pacific Basin. However, these similar relationships have been studied in the Indian Ocean Basin as well with the Dynamo Field campaign, and they haven't found these similar relationships, so there is some evidence for regional variability there. And again, this research is predominantly based on linearly organized convection, but what about nonlinear tropical oceanic convection? This nonlinear convection is abundant in the tropics, and it warrants its own target investigations as well. Additionally, these in-situ studies are largely, again, based in the Western Pacific, as I've said, and with tropical oceanic convection structure and its wind shear relationships varying across the tropics, as we've just described here between the Western Pacific and the Indian Ocean basins, an evaluation of tropical oceanic convection relationships with near storm wind shear necessitates detailed in-situ studies in other regions as well in the oceanic tropics. So some studies have looked at tropical oceanic convection relationships with CAPE, as CAPE is a proxy for thermodynamic instability. The CAPE has been argued to not relate as strongly to convective strength in the tropics compared to, say, the mid-latitudes, just because there's less variable temperature and moisture for a given region for a given time of year in the tropics. That being said, CAPE has been looked at, and ultimately CAPE relationships with tropical oceanic convective structure are inconsistent across studies, even within the same basin and within similar, and using similar methods as well. And so some studies have showed, more isolated single core convection to have greater CAPE than more organized multi-core convection. As shown in this figure by Chudler and Rutledge 2021 here from the Western Pacific. While other studies show opposing CAPE relationships, and other studies show no relationships at all between CAPE and tropical oceanic convective structure. So yeah, a lot of variability exists between the studies with regards to CAPE. The many studies have looked at tropical oceanic convection relationships with relative humidity as well, as moisture content is important for, say, convective buoyancy and thus the development of convection itself. And also air entrainment into the convection, which impacts cold pool strength, rear inflow jet characteristics, and also alters convective buoyancy further as well. So what these studies have found is that the greater the mid-tropospheric moisture, the larger and more intense the convective systems tend to be. And this is arguably the case since greater mid-tropospheric relative humidity translates to less decreased dry air entrainment into the convective systems, and thus less negative buoyancy introduction. And it's notable that these results from tropics here differ from some mid-latitude convection relationships, where dry mid levels are often seen to promote convective development and intensification. And then low tropospheric moisture has been studied at all, and these relationships with tropical oceanic convective structure are found to vary in both strength and sign across tropical oceanic studies, even within similar regions. And it's important to note again that most of these studies of relative humidity are just based in the Western Pacific, and other regions need to be studied in greater detail to evaluate potential regional differences. So in total, the literature shows that near storm mean layer environmental moisture, CAPE, and shear relationships with tropical oceanic convective structure are inconsistent across studies. And multiple studies have suggested that this is probably due to the existence of regional differences in these near storm environmental relationships that may come from perhaps differing synoptic scale climatological differences, different tropical oceanic regions that can influence things such as convective initiation, organization, and microphysics. So with these suggested regional differences, it's important to study a diverse range of tropical oceanic regions. And as we can see here in this adaptive figure of boreal summer precipitation climatology, there have been targeted field campaign studies in the Western Pacific here with field campaigns such as CAMPEX, Togacor, and Quajex, in the Indian Ocean Basin with Dynamo, and in the East Atlantic with GATE and NAMA. Though a lot of these studies occurred many decades ago and thus without the capabilities of modern instrumentation. That being said, however, non-tropical cyclone-related deep tropical oceanic convection and its associated near-storm environmental relationships haven't been well researched in the Gulf of Mexico, Caribbean, and Western Atlantic basins, which is important because as seen in this figure, convection is prevalent in these regions. So targeted studies are needed in this region to better understand relationships with tropical oceanic convection structure and its near-storm environments, and consequently improve model representation and forecasting of convection. And that's really where the NASA CPEX and CPEX-AW field campaigns come into play from 2017 and 2021 respectively. And their overarching goal is to study convective processes using science flights and airborne data sets. And my analysis will cover a subset of the convective cases from CPEX and CPEX-AW that are collected across the Gulf, Caribbean, and Western Atlantic as shown here. And before I go on, it's important to note that all the cases used in my research were collected during a similar time of day, during the evening. So diurnal influences on convective structure are expected to be similar amongst the convective systems, or as I'll call them here on out, convective cases. And yeah, so I won't be discussing these diurnal influences further on since they're all pretty consistent across the cases, or at least assumed to be. So given the much needed targeted sampling of convection in the Gulf of Mexico, Caribbean, and Western Atlantic from the CPEX field campaigns, I aim to answer the question, how does three-dimensional tropical oceanic convective structure relate to near-storm environmental CAPE, relative humidity, and vertical speed shear in various different vertical layers in the CPEX and CPEX-AW observational domain? And so the data I used for my research came from airborne instrumentation aboard the NASA DC-8 aircraft here, which was used for the CPEX and CPEX-AW science flights in and around convection. And there were a lot of science instruments aboard the DC-8s, but the vertically high-resolution data sets are the ones I focused on using for my research, as they record numerous measurements within any given atmospheric layer, and thus they can capture small-scale convective features and environmental variability as well. So the three high-resolution instruments data that I used were dropsondes, which provided moisture and wind profiling, the airborne precipitation radar, which captured high-resolution convective structure, and then finally the Doppler aerosol wind LiDAR here, which also provided wind profiling like the dropsondes. The dawn profiling provided much spatially and temporally denser wind profiling than the dropsondes did. And it's important to note that the dropsonde and dawn wind profiles, in addition to being used to study tropical oceanic convection like in this study, they're also being used to validate satellite retrievals of vertical wind profiles near convection, particularly with regards to the European Space Agency's AOS satellite, which has the first spaceborne Doppler wind LiDAR, which was launched back in 2018. And that was really kind of a big motivation for the CPEX and CPEX-AW field campaigns in general. So combining these three instruments provide really rare and coincident high-resolution near-storm three-dimensional convective structure, wind, and moisture observations, which is a really unique data set, an advantageous data set to have to study tropical oceanic convection relationships with near-storm environments. They're not too common to have all these three things together and co-located. And we can see an example of these three instruments data overlaid here. In this figure, this is just an isolated convective case from CPEX with the APR data obviously being the fill here. You can see some nice convective elements and some nice stratiform elements as well. The dropsondes are the blue barked profiles here, and the Doppler aerosol and LiDAR, or the dawn profiles, are the black barked profiles in this figure. And as you may notice, dawn doesn't always have full profiles. This is due to attenuation of the dawn instrument by thick clouds and precipitation. Nevertheless, dawn still has much greater temporal and spatial coverage overall than the dropsondes do. And before moving on, it's also important to note that all the data in this research was collected conservatively within about 150 kilometers, or about 10 minutes of flight time, of actively precipitating regions, and much closer when considering nearness to convective clouds like anvil cirrus. And so in addition to the airborne payloads, I also utilized coincident satellite data for both spatial and temporal context of the airborne data. Specifically, I used the GPM IMERD surface precipitation estimation product, as we can see examples of here for a single core case and a multi-core case. So I used IMERD for determining the convective type of each sample convective system. Again, it's either single core or multi-core. And then I used GOES IR colorimetry as well for characterizing the life cycle stage of the convection at the time that CPEX and CPEX-AW sampled it. And so it's important to note that the CPEX and CPEX-AW flights weren't necessarily designed to fly within a specific region of the convective system for a long period of time, with observations coming from various different regions of the convection, which really motivated us to contextualize each dropson by a few different categories. So first we characterize each dropson by convective type, as either being associated with an isolated or single core or more cellular system, or being associated with an organized convective system, or that is a multi-core convective system. That's how we define organized convection. Then we characterize each dropson by convective life cycle, the life cycle stage of the convection that it was associated with. So was the dropson deployed into the growing, mature, or weakening stage of the convection. And this is based on APR reflectivity features such as bright band presence and bright band strength, and also GOES IR color evolution of convective core intensity. And then finally, we characterize each dropson by the environment that the dropson was deployed into, as either being in clear air, as we can see an example of here on the right side of the figure, in cloud, as we can see an example of here on the left side of the figure, where it's falling through some anvil cirrus here, or characterizing it as in precip, which, as you can imagine, is it's not shown here, but falling through an actively precipitating region. And it's important to note that the in precip dropsons were excluded from CAPE and the relative humidity analysis due to large moisture biases, although the wind data was still good, so we did use the wind data associated with the in precip sons. So once contextualizing each dropson, then we calculate a relative humidity and wind shear over 4 distinct layers for each dropson. And those layers are the planetary boundary layer, PBL, the mid layer, which extends from the top of the PBL up until the freezing level, the upper layer, which extends from the freezing level up to this uniform upper layer cap, which is about 7.6 kilometers. And this was informed by the lowest maximum heights of all the dropsons in our data set, which were influenced by the different flight levels for the various convective cases. And then finally, the fourth and final layer is the deep layer, which extends just from the near surface up until this uniform upper layer cap, about 7.6 kilometers. So we calculate relative humidity and shear for these 4 distinct layers. And then finally, we calculate most unstable CAPE and mixed layer CAPE over 2 layers, the deep layer and the upper layer. And most unstable CAPE was calculated using the most unstable air parcel found within the lowest 300 millibars of the troposphere, while mixed layer CAPE is calculated using the mean temperature and moisture values from the lowest 100 millibars of the troposphere. So after contextualizing each dropson and calculating their metrics, we first want to identify mean layer CAPE, relative humidity, and vertical speed shear trends for each convective type for the CPEX and CPEX-AW observational region. And we did this by grouping the dropson observations by convective type, with red observations being observations associated with isolated convection, and blue observations being observations associated with organized convection, both in this figure and subsequent figures. And this analysis was performed for dropson data both from all convective life cycle stages, and separately for dropsons just from the growing and mature life cycle stages as sort of a control. However, the results from both analyses were similar, so in this talk we'll just be looking at the analysis and figures that included the dropson observations from all convective life cycle stages. To start out with looking at CAPE, where we excluded the in precip dropson data from the analysis due to the aforementioned moisture biases, what we found is that median deep and upper layer CAPE are slightly greater for isolated convection compared to organized convection, which is similar to the results of Chudler and Rutledge 2021 that we saw a few slides ago. However, as you may notice, there is large CAPE variability within each convective type, within each layer, which motivates additional grouping of the dropson observations by the convective case that they were associated with, and we can see that on the next slide. And when looking at the dropsonde observations, now grouped by both convective type, again red being isolated convection observations, blue being organized convective observations, grouped by convective type and now convective case, we see that there really is no clear relationship between convective type and CAPE for both the deep layer, which is shown here for both mixed layer CAPE and most unstable CAPE, and also the upper layer as well. And again, this includes the in-situ dropsondes, which are denoted by the P's in these plots, which have no moisture biases. Mainly though, it's interesting to note that large CAPE variability exists both between and within some convective cases of similar convective type, even just amongst the clear air dropsondes, which are just the normal points in these plots. Where, for example, mixed layer CAPE varies from 200 joules per kilogram all the way to 1,000 joules per kilogram for just organized convection. And most unstable CAPE varies from 400 joules per kilogram all the way up to 1,200 or even 1,400 joules per kilogram just for case 13 alone. And this variability isn't just because of differing spatial and temporal coverages of the flights and cases, because we see this variability even amongst cases with similar spatial and temporal coverages. So moving on to mean layer relative humidity, where we again exclude the increase of dropsonde data from analysis due to moisture biases. We find that median deep layer relative humidity is slightly greater for isolated convection compared to organized convection. We also find that median planetary boundary layer and upper layer relative humidity are slightly greater for organized convection compared to isolated convection. However, both isolated and organized convection appear to have similar mid-layer relative humidity values, which is unique as many studies from the Western Pacific, for example, show greater mid-layer relative humidity to be associated with more organized convection. Additionally, similar to the CAPE, there is large relative humidity variability within each convective type for most layers, particularly for most organized cases, which motivates additional grouping of the dropsonde relative humidity observations by the convective case that they were associated with, which we can see on the next slide. And when looking at the dropsonde relative humidity observations group now also by convective case, and only looking at the clear air dropsondes, again just the normal points here, we continue to see similar deep layer and planetary boundary layer relative humidity trends with convective type, with deep layer relative humidity still generally greater for isolated convection, and planetary boundary layer relative humidity still being generally greater for organized convection compared to isolated convection. However, now we see that both the mid-layer and the upper layer relative humidity have no clear relationships to convective type. Additionally, as was the case with CAPE, notably large relative humidity variability exists between and within some convective cases, and the large mean layer relative humidity spreads in organized convection that we saw on the last slide can be largely attributed to cases 13 and 16, which have particularly low relative humidity values in the deep, mid, and upper layers, which we'll investigate these two cases later on in this talk. So moving on to mid-layer speech here, where we're now including the in-situ dropsonde data in the analysis, as that data was still good. We find that median deep layer PBL and mid-layer speech here are greater for organized convection compared to isolated convection. These are actually some of our most distinguished trends that we've seen so far with regards to convective type. Although similar to CAPE and relative humidity, large speech here variability does exist within each convective type, particularly for organized convection, which again motivates additional grouping of the dropsonde speech here observations by convective case. And when doing this, again, we're including the in-situ dropsondes in this analysis now. We see that there is a lot of spread in speech here, both between individual organized cases, which could be linked to different types of organized convection, but also within a given case that really isn't tied to the environment the dropsonde was deployed into, meaning that environmental shear can vary quite a bit in the vicinity of organized convection, which is really interesting to see. Regardless, though, we do still find, similar to the box plots, that there still is generally greater deep layer, PBL, and mid-layer speech here for organized convection compared to isolated convection. And so now the analysis I've just discussed and have shown so far has been with regards to the dropsonde data, but we have to remember that the Dawn instrument provides much more spatially and temporally denser wind profiling in non-anvil regions compared to dropsondes. Now that being said, we can only look at deep layer shear with Dawn, as other layer shears require knowledge of the PBL depth and freezing level height, which couldn't be calculated for each Dawn profile since temperature and moisture data aren't available with Dawn. And with PVL depth and the dropsum data found to vary a lot, even within short spatial and temporal ranges, only deep layer wind shear can be confidently calculated for dawn. So anyways, when incorporating the dawn data into our speed shear analysis with the dropsum data, we find that dawn reveals even greater speed shear variability for each convective type than even with what we saw in the dropsum data, and that was a lot to begin with. And additionally, the dawn data reveals that isolated convection actually has greater median deep layer speed shear than the organized convection, which we didn't get the opportunity to see with just the dropsum data. And this change trend is largely influenced by just the single CPEX-AW isolated convective case, which is just this one box plot that I'm highlighting here. It's also interesting to note that this case had some of the highest deep layer speed shears recorded for any convective system sampled during CPEX and CPEX-AW, which is interesting to see. So given the even larger variability in deep layer speed shear when adding in dawn for both convective types, we again further group the speed shear observations by convective case. And we see that near storm deep layer shear variability within each individual convective case now is also further emphasized by the dawn wind profile data, which ultimately leads to less clear deep layer speed shear trends with convective type. And the large speed shear ranges within each case, which are quite interesting and a little unexpected, motivate further investigation into how near storm wind shear and the other metrics for that matter relate to convection, and also why they vary so significantly. Okay, so the prior analysis that I've just done really investigated near storm environmental relationships with two-dimensional tropical oceanic convective structure and large mean layer environmental metric variability within each convective type and between individual CPEX convective cases of similar convective type motivates analysis on how near storm environments relate to vertical convective structure, a result we call it from here on out convective intensity. So we'll first focus on vertical convective structure and intensity analysis of just the isolated convection by comparing frequency of radar reflectivity with altitude between isolated cases with distinct mean layer metric differences, as we can see an example here with upper layer cases 1 and 3. Ultimately, to analyze potential relationships between intensity of isolated convection and near storm environments. So we compared different cases of vertical radar reflectivity frequencies using contour frequency by altitude diagrams, or CFADs, wherein all APR key event reflectivity profiles for each case were binned by height and reflectivity into essentially these two-dimensional histograms with half-kilometer and 5 EDZ bin intervals. And then we normalized each of the CFADs by the maximum bin count in each height layer, and then we differenced the two CFADs to get a plot, as you see here on the left, a different CFAD between the two cases to assess their intensities. Although we also normalized the CFADs by the max bin count in any height layer, and the takeaways were the same. And so what we found out is that the more intense isolated convection had distinctly greater upper layer CAPE. And this CAPE relationship with intensity could be due to, say, greater thermodynamic instability, promoting stronger updrafts or increased buoyancy, which can suspend hydrometers for longer periods of time, thus allowing hydrometers to grow more, essentially. Aside from CAPE, though, we found no consistent trends between isolated convective intensity and mean layer relative humidity, nor speed shear. And so now we'll move on to analysis of how near storm environments relate to vertical convective structure intensity of organized convection, again motivated by large mean layer environmental metric variability within and between now organized convective cases. And we did this again by comparing frequency of radar reflectivity with altitude using CFADs between organized cases with distinct mean layer metric differences. So we can see an example here with upper layer relative humidity between, for example, cases 7 and 8. And we found that there were no consistent shear nor CAPE relationships with convective intensity for organized cases. However, we did find that the more intense organized convective case had distinctly greater upper layer relative humidity. However, this only applies to case comparisons where a distinct difference in upper layer relative humidity existed, which wasn't always the case. Nevertheless, though, this upper layer relative humidity relationship could be due to, say, more upper level moisture being conducive to greater hydrometeor growth via more water vapor available to condense, and also less dry air entrainment into the convective system as well. Additionally, it was notable that there were no similar trends across convective type between convective intensity and mean layer cave relative humidity and speed shear, which may point to single core and multi-core convective systems fundamentally interacting differently within their storm environments. Now moving on, so transitioning. So when investigating large metric variability, both in convective type and between cases, we noticed in particular that cases 13 and 16 had the largest relative humidity spreads of all the organized cases, and some of the lowest mean layer relative humidities as well, as you can see here with deep layer relative humidity and mid layer relative humidity. And this really motivated us looking further into these two cases. So when doing so, we realized that both cases' convective flight legs, as shown here in these figures, had observations encompassing these larger scale moisture gradients and associated with level jets parallel to the moisture gradients as well. And then we realized that both had similar two-dimensional structures, both forming on the moist side of the moisture gradients, and both had both an intensifying sector of the system and a matured sector of the system. So both cases seem to have similar synoptic setups and similar two-dimensional structures. However, when looking at the vertical structure, we saw that even though the two-dimensional structure and synoptic setups are similar, the vertical structure of these systems were completely different, with case 13 in the upper left here being mainly a leading line convective element with trailing stratiform, and case 16 down here having a lot of many embedded convective elements within predominant widespread stratiform. And so this got us really wondering how many near-storm environments relate to differing organized vertical convective structures. And so we'll investigate this now. And so before doing this analysis, we contextualized all of our observations for these two cases as being within or beyond that moisture gradient, with blue observations in the coming plots being observations within the moisture gradient, and green observations in the plots being observations that were taken beyond that moisture gradient. So looking at the mean layer speed shear first, we find that there is no clear relationship between mean layer speed shear and the location relative to the moisture gradient. And then we also found that both cases have similar mean layer speed shear in all layers. We can just see an example of that here with deep layer shear from drops on dawn, case 13 and 16, although case 16 does have slightly greater variability, at least in the deep layer. And then additionally, we also found that the PBL shear within the moisture gradient, so just the blue observations here in this plot, was distinctly greater for case 13 compared to case 16. And this higher PBL shear for case 13 could point to why case 13 is slightly more linear than case 16, which would be consistent with many prior studies of linearly oriented convection in the Western Pacific that I described in the background section. It was important to note that all the PBL speed shear observations for case 16 here are from in-precip dropsons, which are potentially influenced by cold pools, and thus they may not be directly comparable to observations in non-precipitated locations for case 13. So moving on to mean layer relative humidity analysis. For both cases, we found that dropsons within the moisture gradient, perhaps unsurprisingly, tended to have greater mean layer relative humidities than dropsons beyond the moisture gradient, maybe obvious. But with case 16 only having quality relative humidity observations outside of the moisture gradients, because remember we're excluding in-precip dropsons from analysis of relative humidity due to moisture biases. We are just comparing dropson relative humidity observations from the impinging dry air beyond the moisture gradient associated with each convective system. And what we find is that the deep layer is drier for case 16 pretty distinctly compared to case 13. And although this impinging dry air for case 16, even though it's notably drier, it doesn't seem to hinder the intense convection of case 16. And then looking at mid-layer moisture, we find that the mid-layer is distinctly drier as well for case 16 for both our traditional mid-layer definition, which extends, again, includes observations extending from the top of the PBL up until the freezing level, as shown here in this bottom figure. It's also distinctly drier when just looking at the mid-level jet region, which is about from 800 to 650 millibars, as shown in the SKUTs here for case 16 and case 13. And so again, the impinging dry air for case 16, both in deep layer and mid-levels, is notably drier, but doesn't seem to hinder the intense embedded convection of case 16. So now we've distinguished these cases in near storm environments. We can analyze and compare both cases' convective intensities using CFADs and relate the intensities to the near storm environments. So first we identified the intensifying and matured sectors of each case using those IR imagery. We can just see an example of that here with case 16, where 21Z, the eastern half of the system, is clearly more intense than it was 3 hours prior. And then we compared the intensifying and matured sectors of activities and their associated metrics separately for a more fair comparison with one another. So we'll start by discussing the intensifying sectors, intensities, and their associated metrics first. And what we found is that the case 16 intensifying sector is more intense than the case 13 intensifying sector. And however, case 16, its intensifying sector, has lower average mid-layer relative humidities. And again, when we're comparing drops and observations beyond the moisture gradient for relative humidity. And then the case 16 intensifying sector also has lower average deep layer, PBL, and upper layer speed shear. And again, this is now comparing all drops on and dawn shear observations, no matter their location relative to the moisture gradient. Moving on to comparing just the matured sectors, intensities, and associated metrics for each case. Again, we can see an example of that here in the GOES IR imagery for case 16, where 21Z, the western half, is clearly weaker at 21Z compared to just 3 hours prior. So we found that when comparing the matured sectors, the case 16 matured sector is more intense than the case 13 matured sector, even though both sectors had similar mean layer relative humidities and speed shear. And then finally, we ranked each of the 4 sectors, both intensifying and both matured sectors, by each of their mean layer environmental metric magnitudes. What we found is that the 2 most intense sectors, both associated with the embedded case 16 convection, had the lowest deep layer and mid layer relative humidities, but the highest upper layer relative humidities. And both cases overall had similar mean layer speed shear. So it's interesting to see how case 16 is more intense, despite much drier and impinging air in 2 important layers, in the deep layer and the mid layer, that seem less favorable for convective development compared to case 13 environments. Additionally, case 16 forms on the cyclonic side of its mid-level jet, which is again seemingly a less favorable location than the anticyclonic side, which is where case 13 is located relative to its mid-level jets. Again, another seemingly unfavorable setup for case 16, yet case 16 is more intense. However, when looking at low-level convergence, this likely provides us with a key reason for why case 16 can be more intense. So we can see in the case 16 dropsons, skew T's from the northern and southern portions of the flight leg, where the northern portion here we see has near surface northeasterlies, and the southern portion here has near surface southeasterlies. We can see that case 16 has distinguished low-level convergence, while case 13, which is shown here, does not. And this large-scale low-level convergence is likely why case 16 can be notably more intense, despite much drier impinging air than case 13. And overall, this suggests that sufficient large-scale low-level convergence may be enough for tropical oceanic convection to overcome and thrive in otherwise seemingly less favorable environmental conditions. And it may also influence, additionally, the type of vertical structure of organized convection as well. But we'll investigate these questions more in future work to get a more definitive answer on this. Just so to summarize, so using rare, co-located, high-resolution airborne observations from CPEX and CPEX-AW, we found that in the CPEX observational domain, there's no clear relationship between convective type and CAPE. Deep layer relative humidity is generally greater for isolated convective systems or single-core systems, while PBL relative humidity is generally greater for organized systems or multi-core systems. And this PBL relative humidity takeaway in particular is consistent with analysis from both satellite and analysis data, but does conflict with observations from, say, the Quadrix field campaign in the Western Pacific, which could point to some regional variability there with regards to convective type relationships with PBL relative humidity. Additionally, we found that PBL and mid-layer speed shear are generally greater for organized convection compared to isolated convection, and this takeaway is consistent with the literature. However, a lack of deep layer speed shear trend with convective type does differ from literature on quasi-linear convection that I discussed at the beginning of this talk. However, only a few of our organized convective cases from CPEX and CPEX-AW were actually quasi-linear. So it perhaps is not a direct one-to-one comparison there with the literature. Looking at convective intensity, we found that greater upper layer CAPE was associated with stronger isolated convection. Meanwhile, greater upper layer relative humidity was associated with stronger organized convection. And this upper layer relative humidity trend is consistent with observations from the project's field campaign in the Western Pacific. Moving on to case 13-16 analysis, we found that the more intense embedded convection of case 16 had the lowest deep layer, mid layer relative humidities, though the highest upper layer relative humidities, while the weaker leading line convection in case 13 had the opposite. And the mid layer relative humidity trend in particular conflicts with analysis from observations from the Western Pacific and also analysis from satellite analysis data, which is interesting to see the conflict with the literature there. However, the more intense embedded convection of case 16 was located in a region of large-scale, low-level convergence, while the weaker leading line convection was not, so that might be the reasoning there. So ultimately, the take-home messages of this research and this talk are that in the CPEX observational domain, there was large near-storm metric variance, both within convective type and within convective systems as well. And the spatial and temporal coverages of the convective flight legs don't explain all this variability. As case 1 and case 15, for example, isolated cases have large metric variabilities despite flight paths covering small areas. And also these cases have small observation periods as well, sometimes less than 90 minutes for case 15 in particular. We also found that the PBL is the layer most commonly related to two-dimensional tropical oceanic convective structure. And despite inconsistencies regarding specific near-storm PBL environmental relationships with tropical oceanic convection, both in the literature and this study, a majority of studies, including this one, really stress the importance of the planetary boundary layer and its environmental characteristics to the organization of tropical oceanic convection. For example, PBL shear influencing convective linearity, greater PBL relative humidities provide more convective buoyancy or potential energy, or even lesser PBL relative humidity providing enhanced low-level thermodynamic instability, perhaps. So therefore, accurate planetary boundary layer representation in weather and climate models does seem to be critical to improve tropical oceanic convection parameterizations. Additionally, we found that the upper layer is the layer most consistently related to convective intensity. And the upper layer, which again is above the freezing level, isn't discussed too much in the literature, and this study argues that perhaps it should be given more attention. Additionally, a lack of similar trends between environmental metrics and convective intensity across convective systems of different organizations, so single core versus multi-core, does suggest that single core and multi-core systems fundamentally interact differently with their near-storm environments. And then finally, comparing two organized convective cases in depth suggests that sufficient large-scale low-level convergence may allow tropical oceanic convection to overcome and thrive in otherwise seemingly less favorable, for example, drier near-storm environments, and it may even influence convective vertical structure as well. So just to mention a few, some caveats for this research, these results and takeaways, again, are only applicable to the CPEX and CPEX-AW observational domain. But this is also a good thing, obviously, as this area is not well researched with regards to deep non-tropical cyclone-related tropical oceanic convection. Additionally, as is inherently the case with field campaigns, we're working with a small sample size of convective cases, only 12 total, 4 isolated, 8 organized. And additionally, the CPEX and CPEX-AW flights didn't consistently sample convection in a similar region relative to the convection. So we're often comparing observations from different regions of storms, and it also makes it difficult to study how near-storm environments co-evolve with tropical oceanic convection, which is why we really didn't investigate this for our research. And this last issue in particular motivated our strategies for the CPEX Cabo Verde field campaign, or CPEX-AW field campaign in the East Atlantic that took place this past September, where with a similar payload to CPEX-AW, we focused flights on actually sampling specific convective regions and also specific life cycle stages as well. Additionally, almost all CPEX-AW dropsons ended up working properly too, even in actively precipitating regions, which is great. So my future research will look to supplement the CPEX and CPEX-AW analysis that I've done, with convective cases from CPEX-AW, which is in a different large-scale environment in the East Atlantic. And then we'll also incorporate additional convective cases from other tropical oceanic field campaigns as well. Additionally, we'll look to incorporate, in addition to cave relative humidity and speed shear metrics, we'll look to incorporate moist static energy and low-level convergence metrics, as these are important for convection too. And ultimately, this analysis will lead to an interregional analysis of near-storm environmental relationships with tropical oceanic convection. Now I'll further explore these near-storm environmental relationships with tropical oceanic convection structure by running and analyzing idealized tropical oceanic convection simulations using the NCAR CM1 numerical model, where basically I'll be altering input sounding, moisture, and winds that are informed by the CPEX and CPEX-AW observations, ultimately to analyze their effects on convective structure and convective organization. And we can see just an example of one of the simulations I've already run here, which is showing a 25-day simulation of outgoing long-wave radiative flux at the top here and horizontal reflectivity on the bottom here, amongst other variables that we used. I'll also be exploring near-storm environmental relationships from a satellite and reanalysis-based perspective, using co-located archived GPM, GOES, AIRS, and Saphir remote sensing data, along with NASA MERIT-2 reanalysis as well, ultimately to perform an interregional analysis of tropical oceanic convection relationships with near-storm environments, and also an intercomparison of results across data type as well. So do we see similar trends with near-storm environments, both across regions and across data types? Do we see the same environmental variability that we saw in the study with CPEX and CPEX-AW data? And also, how well are the lower resolution, either temporally, spatially, or both, models, reanalysis, and remote sensing instruments capturing important convective processes and features, and also environmental variability that we're seeing in situ data sets from CPEX and CPEX-AW. So we hope to learn more about all of these things in our future research. And so with that, I'd just like to acknowledge NASA for supporting this research, and special thanks to all CPEX and CPEX-AW participants, and also Randy Chase for providing help of coding up the APR data and plots. And a special thanks to Angela, my advisor, for providing just so much helpful feedback, guidance, and support during these past 3 years. And also thanks to Tristan and Angel as well for their help and their feedback for my thesis as members of the GSC committee. And thank you to the members of the High Impact Weather and Tropical Meteorology discussion groups for their valuable input and feedback throughout these past 3 years. And additionally, thanks to Rosa Maria Barrios, George Bryan, and others at NCAR for their help with the ongoing CM1 simulations of tropical oceanic convection. And finally, thanks just to my family and friends for both supporting my decision to go back to grad school, as Angela said, after kind of a 3-year hiatus of working professionally. And just also thanks to them for keeping me sane during these past 3 years during all the work. And finally, just thank you all so much for coming today and for listening. And with that, I will take any questions. Thank you.
All right, student questions for Ben first. Steph, go ahead.
Thanks, Ben, for your talk. I just have more clarification questions. So when you're talking about convective intensity, how exactly are you defining it? Maybe I missed it, but I'm a little confused on what you're looking at to define a storm as being more intense than another. Is it precipitation? Is it the current of lightning? Is it so?
Yeah, so we're defining convective intensity in our case as just having higher magnitude cave and reflectivities throughout the columns, essentially.
Other student questions?
There's-
Juliet, you're online. Yeah, hi Juliet.
Great talk, Ben. This is really interesting. So your conclusion about there not being a large relationship between cave and convective type, I think, is somewhat consistent with our with theory, I believe, in regards to using cave in the tropics, and that not necessarily be like the whole thing about convection being largely stability or used to stabilize in the tropics. And so I'm curious, and you hinted at this a little bit when you were looking at these systems with a higher amount of CAPE compared to others, and that you were suggesting maybe there's some more thermodynamic instability. And so I'm just wondering if you looked a little bit deeper into the environmental conditions for the systems with higher CAPE.
So the trends we had with CAPE there when comparing convective intensity, we also did, again, look at relative humidity and speed share for each of those cases. And CAPE was really the only distinctly different metric when comparing cases, which I think was for the isolated convection. So, the stronger isolated convection only had greater upper layer CAPE, but it didn't have distinctly greater relative humidity or speed share. Does that answer your question?
Yeah, and then I guess also just a little bit into, I think that does answer.
Well, Juliet, were you trying to get at, like, did we actually dive into some of the more details of the conditions during the cases?
Perhaps, and kind of like the evolution of the environment, or just, because I'm a little bit like, well, what was causing that increase in stability?
Definitely, and we didn't look at anything other than these metrics.
Okay.
As I hinted with kind of the low-level convergence, that's something we'll look at for both other field campaigns data sets and also go back and revisit that for all of our cases. And then we'll look at other environmental parameters as well to see what exactly is the reason for that.
Cool, thanks. Hey, you said there's an online question?
Yeah, Ian Corneo said, great talk, first of all. He said, I have a naive question regarding the dropsons. Since they're being released from a moving plane into a sheared environment, does dropson trajectory have to be taken into account? And he also says, what's the typical horizontal distance of a dropson at the top and bottom of the deep layer? Would a sond drop next to a convective cell have biases due to entrainment?
That's a good question. I would say, first of all, the trajectory of the plane is taken out once the dropson data is QC, which thankfully I don't have to worry about doing. That sounds pretty complicated. I don't know the exact horizontal distance that it does travel when falling, but there is a distance that it does travel. So it's not a completely straight up and down vertical profile near the convection. With regards to dropsons falling near the convection and dry air entrainment, it is definitely possible that the dropsons can capture that dry air entrainment. Hopefully that answers this question.
Yeah, we had a lot of issues with the dropsons during these campaigns, so a lot of them even had to be removed. It couldn't even be used. I'd say like, what, a third of the dropsons couldn't even be used for analysis, and so a lot of these potential issues were thrown out, but the dropsons were very problematic, and that was actually resolved during this most recent campaign. So Ben had to work with some of that take into account, but additional issues that eliminated a lot of the dropsons. Yeah, that's a good question. Rudra, then Larissa, did you have your hand?
Yeah, I did, but yeah.
Yeah, Rudra, then Larissa. Yeah.
Yeah, I have more of a basic question. First of all, great talk, I really enjoyed it. So all the plots you were showing with dots and C's and P's, I got confused a little bit. Like, is it showing different isolated cells in a spatial format that you're showing it as a line, or that's just in one convection system and then how it's evolving?
Yeah, so I can just go back to an example of plots. Flash on screen. Yeah, so basically each of these observations along the vertical line here are all associated with a single convective case. Okay. So the data here is the same data that was used to create the box plots, but it's just further separated out by convective type, but also convective case as well.
Okay. And have you thought about grouping the precipitation, the convective, and the rest together?
Yes. Yeah. So we did. We have done that in the past. Just to look at, say, just clear dropsons or just in cloud dropsons, or just in precip dropsons, and we really find similar trends among each of those. Yeah.
Well, and if you go back to that last plot you showed with the scatter plot, the other one,
This one?
you'll notice that there were some cases where most of the dropsons were launched in precip anyway. And so like it was hard to do very much of that comparison because some of the, part of him showing this is some of these were mostly in the precipitating region, and those were the ones that were most problematic with the transmission for this case and some biases. So that's why we were hoping, and Ben was really instrumental in helping decide the dropson strategy for CPEX-AW when we were actually trying to look at convective life cycle to do just the sort of comparison that you're trying to say. That's a little more consistent across cases. Yeah.
Mm-hmm.
Yes. Yeah, thanks, Rudra. Larissa, go ahead.
Yeah.
Yeah, so I have two things kind of related to the water vapor. So I guess I'm curious about whether you have thoughts on some of these relationships with water vapor and which direction the causality might be going, or whether you guys are thinking about that at all, right? Yeah.
Yeah, and it's a good question. I
Yeah.
kind of briefly touched on that and some of the caveats were with CPEX and CPEX-AW, at least for our purposes, we would have liked dropsondes to have been deployed in similar regions or during similar convective life cycle stages throughout the flight. So just like always staying, say, in front of a convective system to see how, for example, water vapor and the convection co-evolve with one another. But we unfortunately, since these observations weren't dropped in consistent regions throughout the flights, we tried to do that comparison and perhaps study evolution of these metrics, but we just couldn't do it with the limited data we had and where they were dropped inconsistently, unfortunately. But this is something that we're going to try our best to do with the CPEX-CV data, which we did have flights that where we did consistently fly in a certain region of convection, or we can separate the observations by convective life cycle stage. Does that answer your question?
Yeah, so like your point there about relative humidity, you don't really have thoughts on whether those, like which direction, like is the
Like is the
PPL
convection influencing the environment?
Oh,
or vice
I see.
versa, like the actual physical
Yeah.
mechanisms, yeah.
Yeah, there has been some research done on that. That's pretty new, actually. Brandon Moulding, if you know who he
Yeah,
is.
I'm familiar
Yeah, he's
with
had a
his
recent
work.
paper that's come out about that. Kind of, it's the chicken or the egg scenario, kind of. My ideas for that, I would guess that for convective initiation, obviously, the water vapor is more of a causal mechanism for initiation. But with regards to further development and weakening of the system, I think it could potentially go both ways. And again, I would refer you to Brandon Moulding's papers. He's done a few papers on that.
Well, I mean, I've known that the causality can go both directions since like my 2004 paper about water vapor precipitation relationships. So like I'm well aware of that. I was just wondering, like in this case, you say like deep layer relative humidity generally greater for isolated tropical organized convection. Like for example, do you think it's isolated because the relative humidity is greater, or do you think the fact that it's spread out makes the relative humidity like kind of a fire hose spreading out throughout humidity everywhere as opposed to just kind of more organized
I would
convection?
think water vapor is more of a causal mechanism for isolated convection. As you said, for broader, more organized convection, I think it's probably the opposite, where just the broadness of the cloud structures perhaps will greatly influence the near storm relative humidity.
Yeah, I think a lot of our clear signs that we had with relative humidity with the organized cells were so far away, like across those moisture gradients, that I don't think they were really representative very well of the environment really close to the convection. So I would take that with a little bit of a grain of salt. Yeah, I think that's what he was kind of getting at. It's a little bit hard to make some of those conclusions from that. Yeah.
Mm-hmm.
Yeah,
Like
but
by
it's a
looking at
really
it
good.
in the
It's a really good point, and we're kind of basing most of our hypotheses a lot around some of the modeling that has modeled some of the previous field campaign tropical data, looking at PBL inflow versus more mid-level inflow at different life cycle stages within organized convections, but we just didn't sample it, I think, well enough to answer that question. Yeah.
Okay. The other thing I was curious about with the relative humidity stuff, right, is that there's known relationships with the amount of precipitation. And I'm just wondering if you made any attempt to kind of control for that. Like the isolated might have less precipitation than the organized convection. So you might actually expect the relative humidity just from that perspective to be greater for the organized convection, in which case this would be particularly notable, this relationship that you have?
Yeah, that's a good point, and something we really didn't think about specifically. But yeah, I think that is something that we'll look at in the future for sure, because that is a good point.
Well, we're at the hour, so if you have other questions for Ben, hopefully you can hang out for a few minutes, and thanks Ben.
Thanks everyone again.